And we covered the lab PVT experiments just now. That was our last topic. And compositions, they are also part of the lab PVT experiment, but we generally don't consider them. But these are just like any other PVT data. These are also measured in the lab, and they have associated uncertainties, which we will talk about during this presentation. So we will be talking about the measurement techniques of the composition. So we have two basic here. The gas chromatography, and we also have true boiling point distillation. You will also see what could be the difference if you have the same sample composition measured from gas chromatography and true boiling point distillation. We will talk about uncertainties quite a bit here in the compositions, because that's something not most people are aware of. And then we have the topic on decontamination. Like how we can do the mathematical decontamination of contaminated samples and calculate the decontaminated composition. And Matthias, my friend, he has a very big passion to present this topic, so he will be doing that topic. The quality checks on the composition, and Matthias, he mentioned yesterday that there are many types of QCs that we generally do on the lab PVT data, including the composition. So we will go through some of them here, but not all of them. And those who will be subscribing this Whitson Academy, we will have a dedicated course there on QCing the lab PVT reports, including the compositional data. So yeah, we will go through the exercise, and this last exercise, Matthias will go through this together with the decontamination topic. Okay, so I think we can start. This is the introductory slide that we saw yesterday, and Matthias went through this very well, highlighting the main key, like the key points on the different experiments, like what are the key deliverables. So we have finished the CC in this standard PVT experiments. The gas EOR experiments will be one topic on day 5 when we will be discussing the applications of the equation of state models. In this presentation, we'll be mainly talking about the gas chromatography and true boiling point distillation. And again, emphasize what are the key deliverables. So gas chromatography, this gives us the mass fractions, or mainly the mass fractions of the different components in the sample composition. And the true boiling point distillation helps us determine the component molecular weight and the density of each component together with the mass fraction. So this helps us to, for example, converting the mass fractions to mole fraction using the molecular weight, and also helps us develop in the EOS model characterizing these heavier fractions, knowing the molecular weight and gravity of the average components. So this is just the brief introduction on the two methods here. Now we will jump into the details and also look at the PVT reports. So yeah, again, these are just some introductory slides. The gas chromatography or simulated distillation is so what we get from the gas chromatography is we generally inject a small volume of the sample into the gas chromatograph, and then increase the temperature of the column. So here you can see the column. And we also have some kind of carrier gas, which could be helium, for example. And as we increase the temperature, the different components based on their boiling point starts flowing towards the detector, and we get a chromatogram. So yeah, so we get this chromatogram, which we analyze and calculate the areas of each peak, and which relates to either moles or the mass of the different components present. The gas chromatography doesn't give us any physical, it doesn't give us any information on the physical properties, for example, the molecular weight density of the different components. It only provides us the mass distribution of the fluid, the component mass distribution, or if you have, depending on what kind of detector you are using. So if that's one kind of detector, the flame ionizing detector, which gives us the mass fraction, and if you use TCD, which is thermal conductivity detector, I guess. So that gives us the moles of the different components. Just brief on the history. So when in the pre-1980s, when PVT labs, they were doing the compositional analysis, we used to only get one heavier fraction, that's the C7 plus, as one pseudo fraction, and we had all these lighter fractions C1 to C6, and then non-hydrocarbons S2S, CO2, and nitrogen in the compositional data. We didn't have the extended GC analysis, including like heavier fraction, like now usually we get like C30 plus or C36 plus as the heaviest fraction. So now this is in the recent reports you can find. I guess I'm sharing, right?
Yeah, I see it, the list.
Yeah.
I see.
Yeah. So
It's fine.
we're sharing a screen here, so maybe just try to log in and log out again if it's frozen on your end. Yeah. Perfect.
Thanks. Yeah, so in the recent reports, the PVT studies, what you find out that you have the same lighter hydrocarbons, and for the heavier hydrocarbons, we get more resolution. So we get these isomers of this single carbon number C7. Will you do it? Okay.
Yep.
C7, C8, and C9 components. So you get, for example, methyl cyclopentane, benzene, cyclohexane, and normal C7. So these isomers here, also some isomers for C8 and C9. And then we have usually single carbon number components until C30 plus or C36 plus as the heaviest fraction. And the single carbon number components, the definition of the single carbon number component C7 is not based on how many carbon numbers are there in the component. So let's say if we have benzene, for example, so benzene is C6H6. It has 6 carbon numbers, but it is part of the C7 component. Because the way single carbon number components are defined, that definition is based on the boiling point of the component. And by definition, a single carbon number component CI is consists of all the pure compounds that boils off between the boiling point of the normal paraffin of that component. So, for example, all the components that boils off between normal C7 and normal C6, and normal C6 is not part of the C7. So everything that boils off higher than the boiling point of the normal C6 until normal C7 is part of the single carbon number C7. So these are all the components here for C7, and then we have these components here for C8. So that will be our C8 component, for example, and then we have C9 and C10, for example. Yeah, so that's something we have went through. Yeah, and that's something we already know, that the single carbon number component. So if it's C7 only, or C11, for example, if you have isomers in the lab reported data, that consists of many different compounds of the different types. So the different types usually we have is one is aromatics. You can have naphthenic compounds. We have normal paraffins. So as an example, benzene is an aromatic compound in C7. You have a naphthenic methyl cyclopentane in the C7 group. So these are all the different pure compounds in a single carbon number C7 component. and the relative the component properties, because now this is a pseudo component, right? So because this is single carbon number consists of many pure compounds, the average properties of this single carbon number component, it depends on how much is the contribution of the different type of compound in the total makeup of the single carbon number. So what is the relative percentage of benzene, for example, is present in the total single carbon number compared to normal heptane. And that may vary from one field to another, one reservoir fluid to another. And that's the whole objective of the C7 plus characterization that we will go through tomorrow. Yeah, so the percentage contribution, which we usually refer as relative aromaticity per affinity, that is usually known for these components, C6 to C9, sometimes C10, if the lab is reporting isomers, all these isomers that we saw before, but they are not known for the C11 plus fractions. And we try to find or come up with some average properties with the proper C7 plus characterization workflow that we will see tomorrow. And that's very important for our EOS model development. Okay, so now we jump into the procedures, like how we measure the compositions, and the first we will discuss how the compositions are measured for low pressure gases. If you have a flash gas, like which is at ambient conditions, or a separator gas, how the compositions are measured for those samples. So the gases for those gases, we don't have much of these heavier fractions. C10 plus, for example, is essentially 0 in the flash gas or the separator gas. And usually the detector that is used is the TCD detector, because we have these lighter components, nitrogen, C1, C2, and we need accurate measurements of the areas of those components. So yeah, so we have this is something we have already gone through. We usually put a small volume of the sample into the gas chromatograph. We get the signal, which is the peaks of the different components, and that's just the baseline, which is the response of the gas chromatograph. So that's the baseline, which is the response of the chromatograph when you are only flowing the carrier gas. And we measure all the areas of these components with respect to the baseline, and so in that case, if we have gases which doesn't have essentially these heavier fractions, all of the components elude out from the gas chromatograph. So we can measure the area of all the components, and then the sum of all the areas is actually the total area of the entire signal, and we can represent the mole fractions of the different components as the ratio of the area of each component divided by the total area of the signal. We also measure the gas gravity and calculate the molecular weight of the average molecular weight of the total gas, which is simply from using the molecular weight of the air. The mass fractions, we can convert the moles to mass fractions simply with this relationship, knowing the mole fractions, the individual component molecular weights, which are known for all the components here because these are essentially pure components, and the average molecular weight of the gas coming from air, for example. And gas compositions, usually we believe that there are no uncertainties in the measurement itself. So there are usually, because it's very simple system, no heavier components and no problems with the GC usually. So now we will talk about how the oil compositions are measured. And
just a comment.
Yes.
What do you mean with no uncertainty in the measurements of the gas chromatographs?
Yeah, so when I mean no uncertainty, it means that like we will discuss the reasons of uncertainties later. Like you have the baseline shift and internal standard that we use, and you add those uncertainties there. Those uncertainties are not present, for example, here in the gas analysis.
Because you have the instrument uncertainty when you do the analysis on the component. So you cannot say, for me, you said there's no uncertainty. Of course, there's uncertainty because the gas chromatograph has some uncertainty limits there. So, and this is based on ASTM standards, that if you run a sample, you know that this component with that kind of concentration have uncertainty of plus minus some, So for me, it's not neutral that you have none.
No,
you have some uncertainty because you have your instrument and you do the measurement there, but that's explained by if people want to that we can just give them because this is based on standards in ASTM standards. Yeah,
it's a very good point actually. So it's actually a wrong choice of word. No uncertainty. There are actually no lab measurements without any, like any measurement in the lab will have some associated uncertainty. But the point here is that the measurements of these, the uncertainty is quite low compared to the uncertainty we have in the oil compositional measurement.
That's correct. That's correct. Yep.
Just a comment also on that. I appreciate that that statement. It's exactly true, and Bilal is correct in saying that I think it's low relative to the other uncertainties in compositional data of the oil. Now, having said that, the low pressure oil, particularly the flashed oil, will have heavier components in it because the K values at 1 atmosphere for C6, 7, 8, 9, 10, maybe through 11 and 12 are actually increasing quite a bit. And if you do that flash, the single stage flash to measure compositions, if that flash gas is done at a higher temperature, for example, to avoid wax precipitation, then you get even more of those components. Having said that, the heavier components that you get in that gas, in the flash gas, are still lighter than, let's say, where the baseline shift starts. They are going to be eluted and quantified by the GC with a high degree of accuracy. So it's not right to say that they're not there, but they're there, and what are there in the way of C6 to C12 components are there. They're quantifiable. So they are there, and they can be quite significant amounts because the specific gravity of that flashed oil can be 1.5 to more than 2, and that those the high specific gravity of that is because of these C6 to C12 components. But still, you're able to resolute out the amounts of those components quite accurately, I think. It's just kind of a detail.
Yeah. Very good, Curtis. And Hans, very good comment. And thanks for the correction here. Okay, so now we jump into the compositional measurements for the stabilized oils. So we were discussing a few terms like baseline shift, internal standard, and those of you who are not aware of those terms, we will go through them here now. So stabilized oil, that can be your surface oil from the flash of the separator oil. We saw it in the PVT report. We will again see it one more time when we go through the PVT report. Or we can have the flash oil from the flash of the bottom hole sample or MDT sample in the PVT lab. That's part of the compositional measurement, and we will see later on how you measure the compositions of separator oil, bottom hole sample, or MDT samples. So one fact about these surface oils is that you have large amounts of C7 plus fractions. Essentially, you have about more than 90 mole % is is usually the C7 plus fraction in these surface oils. And we use the FID detector, and the measured areas in that case are proportional to the component mass. And we have the same principle as we used for the gas, but now we have two problems. One is the baseline shift. So baseline shift, as I mentioned earlier, that it is actually, yeah, so here you can see this is the figure taken from the SP monograph, that you have a chromatographic baseline, which is the response of the chromatograph, and you only flow, for example, the carrier gas. And you can see that these component areas they are started shifting up as you increase the temperature, and you need to account for this when we are computing the areas. And generally, the areas that are higher than, for example, C15 component, those are generally affected due to baseline shift. And the other problem, so that's one problem, the baseline shift, the areas of very heavy components, C15 plus or C25 plus, somewhere between that, those are affected with the baseline shift because this baseline shift is continuously changing. And also the second problem is that you don't get all the material out usually from the gas chromatograph, because there is always some residue left. And due to that, what happens that you don't know the total signal area. So the total signal area, that's the AT, that's unknown, because the area of that residue, that's the N plus or C36 plus, or C30 plus, that's unknown to us. So to resolve that problem, what is done usually it's that for the gas chromatography we use a special component which is called internal standard. And so here you can see, for example, the internal standard. This is the peak of the internal standard component. So this is a separate component that is added together with the sample, and you know what component it is, and you know where the peak of that component will form in the chromatogram. So you get the area of that component, and we know how much mass of that component we have input, for example, in the chromatograph. So you can get the total area of that of the signal from, for example, from knowing the total mass of the sample that we have input, and here is the total mass of the entire sample that we have input in the chromatograph, and we also know the area of the internal standard and mass of the internal standard. So knowing this information, we can compute the total area, and then once we know the total area or have the estimate of the total area, we can calculate the area of the heaviest fraction or the residue that's left in the chromatograph, which is simply back calculation. So you know the total area, and then you can calculate the areas of all components until that residue. So let's say that could be your C35 component or C29 component. And now here you see that we have these plus minus bars everywhere, because we know that individual component areas, they may be affected by, for example, for some of the components. And the total area, it can also have some uncertainty due to the internal standard, because it's not a perfect, in a perfect world, there would be no error in knowing how much mass of internal standard you have input, and calculating the total area of the internal standard and the total area. So you always have some uncertainty here, you have uncertainty here, and that all these uncertainties actually add up to the uncertainty in the heaviest fraction amount. So the heaviest fraction amount is always more uncertain compared to the amounts of all other components. And the lab reported mass fractions are just the ratio of the area. So area of each component divided by the total area that we got from the internal standard. Yeah, Hans?
Just a small comment from the baseline shift.
Yeah.
Normally, laboratory, they are running what they call a blank run. It means it's a run with not adding any samples at all, just to see the shift of the baseline. And then we subtract the baseline, try to compensate for this baseline shift. It's not. It's better to do not to do it, but we normally when we run analyze the samples, we just take one blank, two samples, one blank, two samples, and then we're using that blank to subtract the baseline, trying to compensate for this baseline shift.
Yeah. So that's absolutely right. So you have to compensate for this baseline shift and do the correction, as Hans is saying, to get the right component areas. Yeah. Thanks, Hans. Yeah, so when we look at the PVT reports, we look at these mass fractions reported for the flashed oil. We should be aware that those measurements, the flashed oil composition, may have uncertainty due to these calibration errors, which
Gulnar have a question.
Yeah, Gulnar. Sorry.
Yeah. If we take live oil, for example, and what we're doing here, we basically separating, we flash it, right? And then we have the gas, which goes through the gas chromatography, where you explained, and we measure through the GC composition. And then after flashing that oil, the stabilized oil goes through this FID, right?
Yeah,
if I understand.
It's the gas chromatography with an FID detector. Yeah.
All right. Yes.
Yeah.
Okay, good.
Yeah. So that's exactly right, and we will see, because now we are just these are what we are discussing now in terms of the compositional measurement. It's just how you measure the composition of the different products that you get from the flash, and we will see how this information that we are discussing now can be used to calculate or determine the composition of the samples that we are interested in, which is separator oil sample composition or bottom oil sample composition or the recombined sample composition. That's something we will discuss in the coming slides. Very good, Gulnar. So these uncertainties here, so we should be aware that these mass fractions in the flashed oil can have uncertainties due to these two issues here, and also now we should be aware that the amount of the heaviest fraction has the most uncertainty, because it's the area of that component is back calculated, and all the uncertainties may add up to that component area. And again, for all for the equation of state model calculation, we know we cannot use the mass fractions, so we have to have mole fractions. And to get the mole fractions, we can convert the mass fractions knowing the individual component molecular weight and the average molecular weight of the flashed oil. And each of them have uncertainties, which we are discussing here. So the lab measured average molecular weight of the flashed oil can have uncertainty 5 to 10% or even higher sometimes. And individual component molecular weights, we were already discussing this before, that these heavier fractions, we have to come up with average properties, right? And those the component properties for those heavier fractions can vary from one field to another. PVT labs, they generally use some arbitrary lab-specific component molecular weights, which may or may not be representative of the field. So there is some uncertainty that comes from the choice of the molecular weights PVT labs use to convert the mass fractions to mole fractions. And again, the molecular weight of the heaviest fraction has the highest uncertainty, because it's usually, it's the most unknown compound, and you the molecular weight is usually back calculated knowing the average molecular weight, the mass fraction, and the individual component molecular weight. Yeah, so now we will talk about how the compositions are measured for the pressurized samples, like the samples we generally are interested in, and knowing the compositions. And we use their composition in EOS model development, for example. So meaning that how you measure the composition of the separator oil, the separator recombined fluid, for example, the MDT or the bottom hole samples. So for any pressurized sample, the procedure is the same. You take the total composition, the total sample, either separator oil sample or recombined fluid, and we flash it to the ambient condition. And this ambient condition, that this process of flashing, it can vary from one lab to another. For example, you can have a cryogenic flash, for example, to get more accurate liquid yields from the gases removed. And once we flash that, we measure these two products, the composition of the two products, the flash gas. So that's the flash gas. You see G with a hat again. That's the surface gas. We measure the composition of that flash gas and also the flashed oil. And we also measure the amounts of each phase is being produced. So that gives us the GOR of each phase, the total GOR of the total composition. And that GOR measurement can have uncertainty up to 5% or even sometimes higher. Like for example, if you have very lean gas condensate, then this due to very small liquid volumes, you can have this uncertainty that may be even higher than 5%. Yeah, so this is something this process of measuring the composition of the pressurized sample, we generally term this as flash GC recombination, because what you do is you first flash the total sample, you get the two products, you do the GC analysis of each individual phases, the gas and the oil phase, you do the GC, and then you do this mathematical, so these are 3 steps. You do the mathematical recombination of the flash gas and the flash oil using the measured GOR to get the total composition that you have here in the PVT set. So the composition that we get from the the total composition that we get for our samples, separator oil samples or the recombined samples, that can be calculated with this equation, which is simply using the flashed oil composition that we have measured, and FGW, that's just the gas fraction or the vapor fraction in terms of weight or mass, and you can calculate that from this equation that we also saw. We saw the equation in terms of the molar fraction, but this is the mass fraction, mass vapor fraction, and it can be calculated using the density of the surface oil and the molecular weight and also the GOR. And now you see that this composition that we are interested in has uncertainties due to many reasons now. You have uncertainty in the flashed oil due to baseline shift and internal standard. You have some uncertainty here in the vapor fraction because of the GOR. So all these uncertainties add to the uncertainty in this total composition. And most importantly, that these weight fractions, we generally don't use them. Like we need to have mole fractions for example, for equation of state calculation. And again, you can convert the mass fractions that come from here to the mole fractions, again, knowing or using some arbitrary component molecular weights, and the average molecular weight is simply can be calculated from this equation, knowing the mass fractions and the individual component molecular weight. So this mole fraction now have uncertainty, not just because we have uncertainties here, but also there's some uncertainty in the average molecular weight and in the individual component molecular weight. Yeah, Gulnar, sorry.
Yeah, in your previous slide, you showed us the flash. So my question is, will flash condition affect the result of the GC. For example, you heat up until 80 degree, or you heat up until, I don't know, the reservoir temperature, which is 60 degree, or you do it at the ambient, at the room condition.
Yeah, so you mean that if you do a flash at different temperature than ambient temperature, does it affect the composition we are calculating here?
Yes.
The total composition, right?
Mm-hmm.
Yeah, so it should not affect the total composition, because if you are doing the flash at elevated temperature, then maybe your the flashed oil composition or the flash gas composition will be different than the flashed oil and flash gas composition you get at the ambient condition. But your GOR will also be changed based on the temperature that you are flashing, I guess. Yes, Hans?
Yes, that's correct what you're saying. The flash is dependent of the temperature you are using in the flash. And of course, if you compare two flashes with different temperatures, you will get different gas composition and different oil composition. But when you look at the recombine it should be the same.
Yeah.
I have seen that once before when I compare a lab doing the flash and they're doing it, I understand nothing. But when I asked them, they had done one flash at 48 degrees and one flash with 15 degrees. Yeah. And that's explained why we get different kind of there, but the total should be the same.
Yeah. And so that's one example of the different flash temperature. But like this is like this cryogenic flash. If you look at this experiment, how this is done, here you actually cool the entire sample that you are flashing with a liquid nitrogen. So you see what crazy temperature you will be having during your flash, and you get the very different flash gas and flash oil compositions, and those are not in equilibrium because the temperatures are changing quite a bit. But again, the total composition that you will get should be the same, because the GOR or the recombination ratio will also be reflected because of these pressure and temperature changes that you are having during the flash.
Okay, thanks.
Yeah, thank you very much, Milnar. So we were here. Yeah. So if we just summarize all these uncertainties, the reasons for these uncertainties, we should be able to understand now that the total mixture composition, the molar composition that we see in the PVT reports, we use in equation of state model calculation. We generally just take the lab reported data and dump it into the PVT package and just start doing calculation and believe that everything is accurate with 3 to 4 significant digits on the composition. That's not the case. Because the compositions are just like any other PVT data with associated uncertainties. And those uncertainties, the main reasons are you can have uncertainties due to baseline shift and internal standard, which is affecting your flash oil compositions mainly. There you have a recombination GOR uncertainty affecting the recombined composition. And then you have also uncertainty in the choice of the molecular weights that you use to convert the mass fractions to mole fractions. And again, the amount of the heaviest fraction should be considered as the most uncertain always, because of the high uncertainty in the mass fraction back calculated from all other areas, and the component molecular weight, which is also again has the highest uncertainty. Okay, so the question is why should we care? Like we presented like 5 to 10 slides on this compositional uncertainties. Why should we care about these uncertainties? So the most important reason is that this composition that we are talking about here, this is an input to your equation of state model, and it affects all the PVT calculations that you are doing for that particular sample. And if these uncertainties, we should account for all those uncertainties while tuning the EOS model. So generally that's not done, because generally when we tune the EOS model, we we generally consider, okay, the compositions are very accurate. There are no uncertainties, and we generally try to change the EOS parameters to match the PVT data for a given sample. But that's not something we do internally at Whitsun. We account for all these uncertainties that we have talked about while tuning the EOS model, and allow very small slight adjustments in the composition while tuning the EOS model. So we define, Curtis?
Yeah, just making the adjustments are made to reflect the laboratory uncertainty.
Mm.
So I think that's an important point to emphasize here. So
Yeah, so when we define the composition, and you will see tomorrow when we will be doing the exercise, there is a very comprehensive exercise on how we treat the compositions while developing the equation of state models. And you will see, as Curtis rightly mentioned here, that when we treat these compositions, we try to account for all these uncertainties that we have in the compositions, in the measurements of the composition. So when we define the composition, we always honor the lab reported mass fraction, because we know that those are measured and not the mole fractions, especially for the flashed oils. There we have more uncertainty, and then we allow small adjustments in the amounts of these the mass amounts of these heavy fractions, where we have more uncertainty due to baseline shift or internal standard. And that's something we will discuss later when we also allow small adjustment in the recombination GOR within the uncertainty limits we have. That alters the total composition slightly from the lab reported data. And we do the conversion of this mass that we have honored here, the lab reported mass, to moles using some consistent field representative sets of individual component molecular weights that we have in the EOS model. And again, tomorrow we will do the exercise, like how for the particular case we have the PVT reports, how we can come up with more representative molecular weights, which may slightly differ from the lab reported component molecular weight. Yeah, and usually the rule of thumb for us internally, like when we do these compositional adjustments, they are usually very small, so less than 1 mole %, for example, in the methane or the total C7 plus content, which is usually the exists in the heaviest in the largest amount. Yeah. Yeah. So now
maybe I could just give an interesting kind of historical commentary about these compositional adjustments.
Yeah, Curtis.
This is something that was implemented into the PVT software that I wrote back in the mid-1980s called PVTX. It's now marketed and sold by Roxar. And the compositional uncertainty in that program was reflecting only one of the uncertainties in laboratory data. And that was the molecular weight of the C7 plus, which was known to have a fairly large uncertainty, plus minus, in the best case 3%, and in the worst case 10, sometimes 15%. And that molecular weight of C7 plus molecular, that uncertainty there would affect the mass to mole conversion for all components. So 10% error in that number, being 200 instead of 220, for example, would then affect maybe 1.2 mole % error in methane, less for ethane, propane, and it would change all of the, it would make all of the mole % for all the components wrong, not just the C7 plus. So it was an important, let's say, uncertainty to consider. That same method was introduced well, both in a paper that we had in 89, I think it was, And in the same book on C7 plus characterization, it was a collection of articles on C7 plus characterization in 1989. Both ourselves, who had this in PVTX software, and independently, CalCEP in that paper they had in the same book also introduced the same method for converting mass to mole percent and the uncertainty in this C7 plus molecular weight. So it dates back a long time, both accepting there's experimental uncertainty and that it can have a consequence on the molar composition. So in today's PVT sim, for example, you have this option. However, what Bilal is going through now and what we know in the laboratories know, the uncertainty in molar composition reported in the PVT report is not limited to that one uncertainty.
Yeah.
And so what we're going through now is a more comprehensive quantification of uncertainties from really three primary resources that he's going through here. So it's just kind of it's an important and interesting, I think. You can't say, or CalCEP can't say, well, oh, you can't make these changes because we don't make them. That's not an argument. The argument is that all PVT software should allow smaller adjustments to reflect the true laboratory and experimental uncertainty in compositional data. And that's what we're trying to go through here. And we see it time and time again being important for getting a reliable, consistent equation of state model that describes all of the samples in a field, not just one sample. If you're only going to match one sample from a field, you probably don't need these various compositional uncertainty knobs to turn. Probably would be wrong to do it as well, having only a single sample. But when you have 10, 30, 50, 100 samples with PVT data for each sample is going to have a different level of a backdrop, a little bit of history on this. And we find it very, very important to developing these multi-sample EOS models.
Thanks, Curtis. Okay, so I think now we can get started with the exercise here. So we have an exercise on doing the QC of the laboratory composition. So we'll be mainly doing the recombination QC and also this conversion from mass to mole. That's exercise 8 here. So and the data that's shown here in this Excel file, that's from the oil PVT report. No question. Yeah. So that's taken from this oil PVT report. So we have, and that's bottom hole MDT sample. So we have the flash gas composition and the flash oil composition, and maybe I can in the report. Yeah. So this is the oil PVT report, and you see you have a reservoir fluid composition, bottom hole sample. So that's why you have the flash gas and flash liquid recombine mathematically to give you the reservoir fluid composition, which is this here. So we have taken the flash liquid and flash gas composition, the mass fractions, in this Excel file here, and we are going to calculate the total composition and then compare it with the lab data. So we calculate the total composition in terms of mass and also moles, and compare with the mass reported by the lab and the moles reported by the lab. And to do that, so we have this data here from the flash of the bottom hole sample, the flash GOR, the oil density, the oil molecular weight, and the gas gravity. So first, we can calculate the molecular weight of the flash gas, which is this multiplied by the air molecular weight, 19.7. And then we have the oil mass. So the mass is the density times volume, and volume we can take 1 barrels of basis here for the flash oil, so that the flash GOR will represent the gas volume, which is 307. So using 1 barrel of oil at the standard condition, surface conditions, the mass of the oil will be simply density times volume. So density is the flash oil density here, which is in gram per cc. So we multiply the 62.4 to convert it into LV mass per cubic feet. And then we have the volume, that's 1 barrels, and then multiply the barrels by 5.61458 to convert into feet cube. So that's the mass of the oil, and then we have the mass of the gas, which we can calculate from the ideal gas law, because it's at standard condition, the surface. So PV equals to NZRT. So the mass will be the pressure, which is 14.7 psi, times the molecular weight divided by RT, so 10.73 multiplied by 520 Rankine, and multiply with the volume. That's this number here. And then we calculate the FG, that's the recombination ratio on a mass basis. That's FGW, so that's simply here, also shown here, that the mass of the gas divided by the total mass. You can also use the equation that's given in the formula sheet. That's just a direct equation, but here we are just decomposing that into its different constituents to make it more understandable. So that divided by the total mass. That's the calculated FG, and we can also calculate the lab reported FG, which is this equation here. And this is rearranging this equation here, which we showed in the PowerPoint. So just rearrange it for the FGW, and then use the lab reported compositions to calculate the lab reported FG. And we can just take one component. Usually methane is good enough because it has the highest amount with more significant digits. So let's take that here. So if you take methane, for example, minus this number here divided by this, the flash gas and the flash oil. So you see they are very close. And so that one key, you calculate the FGW from this information here, and then compare it what the lab has used in their recombination, and these are like very similar here. And now we calculate the total recombined composition. Now we have the FG value. So using the lab reported FG, lab reported flash gas composition multiplied with the calculated FG here, and then just log that, and then plus 1 minus FGW times FLO, the flash oil composition, and then we just drag that down, and then you can compare column H versus column I, and this should be essentially the same, and you can see they are the same. So that's how the lab reports the recombined composition. And now we can calculate in terms of moles. So to calculate the mole percentage, we have already calculated moles here, which is simply the mass divided by the molecular weight of each component. So these are the moles of each component here. These are the moles of each component here. And now that's the sum of all the moles. Yeah, sum of that column here. So if you want to calculate the mole percentage or mole fraction, then it's simply the mole divided by the total moles multiplied by 100. And then, yeah, this has to be locked in here. Okay. Yeah. And then you can compare this with this column, which is yeah, almost the same, the two here. So that was a small exercise on the recombination QC of the PVT data of the lab reported compositions. And again, like we are not going through the other QCs that we generally do in the lab reported composition, because then it will take like 1 or 2 days just to go through the QCs on the compositions only. So, okay. So, are there any questions? Yeah. Okay, so I guess we can jump to the next topic. That's the true boiling point distillation. We finished the gas chromatography, yeah. So in the true boiling point distillation, what's different compared to the gas chromatography is that you do actual distillation of the the sample by vaporization. So you start heating that's kind of an equipment shown here. That's from the monograph. So you have a sample here in this flask here, and then you just start heating it up, and then you collect the vaporized samples in these containers here on the top, and the temperatures that are specified usually for doing this distillation, it depends on what kind of analysis you want. You can specify temperatures that can give you single carbon number cuts or refinery cuts, etc. So that's completely, yeah, it depends on your request, what kind of analysis you want, and the different analysis have different names of the experiment. So if you like, for example, if you want the single carbon number cuts, then it's ASTM D2892, for example. There are standard procedures for doing the experiment, and the different cuts or the samples that are collected for the analysis at each different temperature intervals. Those cuts are analyzed for measuring the molecular weight, for example, the density, and also you also measure the mass of each cut or each fraction that is distilled at a given temperature interval. And so you measure the physical properties of these properties, molecular weight, gravity, and the physical properties of the last fraction, the residue is often from the material balance. And you can see why you need more volume. Like if you true boiling point distillation requires large volume of samples, because you want to do the physical distillation of the entire sample and want to measure these properties, the physical properties of each individual cut. So that's why the true boiling point distillation is not generally done. It's like gas chromatography. It's almost always done to measure the compositions, but we recommend to have at least one set of true boiling point distillation for a given fluid system, so that you have information on measured molecular weight, density, and the normal boiling points of the of these heavier fractions that can be helpful in the characterization of the heavier ends. So from the GC analysis, the gas chromatography, you don't get any information on these physical properties. And for EOS calculations, we need both the amounts and also the properties of each fraction. That's something Matthias mentioned on the first day, that EOS models, they need 3 inputs like composition, pressure, and temperature. And there are 2 tables. One is the component properties, and we need this. You need to have this information that can be very helpful in estimating the properties of those heavy fractions. Yeah. So this is an example of the true boiling point distillation data. So you have here, these are the temperature intervals. So for example, the initial boiling point to 97 to 156 degree. You have the how much percentage weight percentage of the fraction is removed or distilled off, and the specific gravity of each individual cut. What is the associated carbon number? For example, if you're doing it on a single carbon number basis, as this experiment here, then so C6 carbon number has this boiling point interval. C7 has this boiling point interval. And then you have the measured molecular weights on the right. And then this last one, that's the residue. That's usually, you can do, that's usually from the material balance, knowing the total mass and the density and the molecular weight of the sample. Yeah, so the TBP analysis is not generally done on every sample because it requires large volume and is expensive. Then of course the GC analysis. And these are just some extra slides which you can look at. Okay, I now we are jumping into this decontamination topic, and there are some additional slides. So Matthias, would you like to come here?
Yeah.
So my throat can get a little bit rest for the rest of the day.
By some fishermen's friends. Yeah, so this we have 2 slides here just for trying to bridge the gap a little bit for those of you who haven't worked that much with compositions, as Chris and Bilal and Hans and others here in the audience. There are also a few folks that haven't been exposed at least that much to compositions. We have a few slides here just to try to bridge the gap between these compositions and actually lingo in day-to-day life. So, for instance, what's the difference between LNG, LPG, NGLs, etc., which I'm still struggling with myself sometimes. So it's just the purpose of this slide is just to give an overview of the differences and kind of a little bit give to what compositions is going into which products, and also what these different types of components are actually used for in the real world. The ones that Bill talked about, many of them, but some are used for heating, like methane. Some is more used for plastic purposes. Propane and butane is typically used for heating. Some cases also plastic for propane, and actually C3 to C4, which I didn't know was actually in some parts of Europe used as a fuel, like autogas in Turkey and also parts of Australia, for those of you who have been there on vacation or lived there in the past. And when we talk about C5 plus is typically what we fill our cars with, so gasoline and various kinds of fuel, whether that's jet fuel or others. The next topic we'll cover, and what I actually wanted to do on that topic, which is decontamination, is to go through the topic a little bit like how we go through this topic typically, and then we're great to actually get some since we have Hans there with us from the lab, just how they are dealing with contaminated samples and in practice to put some spice on this particular section. But this is just a recap slide from, we actually went through this slide yesterday, where we talked about the difference between the non-hydrocarbons, the pure compounds, the single carbon numbers, and we also mentioned briefly there typical range. Obviously, that'll change from what the oil-based mud you're using and what service company you're using, etc. But typically, the oil-based mud compounds are between C12 to C20. And when it comes to drilling, I guess, with oil-based mud, and you're producing a sample, or you sample from that well and you bring it to the laboratory, you might risk actually getting a contaminated sample, and sometimes a very contaminated sample. This is just an example of a 99% contaminated sample, looking at mainly the heavier components from C7 and up to this is probably some kind of C plus in the end there. But we clearly see a hump here between C12, I believe, and C20. And as the contamination level is reduced to 50%, we see this hump is getting smaller, and at 2% versus no decontamination level, it's actually very small difference. This, I guess, these slides are just made or constructed with some data, but we see even with synthetic data, it can be hard to differentiate graphically whether a sample is contaminated or not. So we actually have this Excel example that we like to show as a part of the class, where we are together as a group trying to, and that probably works better in the live courses, but we'll try anyway. There's nothing to lose on that. Where we together are going to try to find a decontaminated fluid composition for a synthetic case, and actually see how difficult that can be in practice. But before we go there, just the basis for, I guess, how this decontamination work is done. So this is a little bit simplistic, and how we deal with it in practice is a little bit different. But the basis for this is that you at surface are producing some kind of contaminated fluid composition, and mainly here we're using the symbol X, and the reason for that is that the stock tank oil or the separator oil is what actually has the components that are in this range from C12 to C20, where mud contamination is relevant. So that's why we use the symbol X. And then this, we know that what we're producing, a potentially contaminated sample, is some combination of a mud composition. So this is the composition of the mud, and the actual stock tank oil composition. And actually, what we would like to back calculate is this guy right here, because that's the true in situ or reservoir representative oil composition. But one thing that we can measure this, so we can get the mud composition from the service companies, so we know that one. We can measure this with the different procedures that the Bilal just talked about. We want to get this guy right here. But in general, we don't know exactly what this mud contamination FG is. So essentially the vapor, or not the vapor, but the mud mole fraction. That's what this is. So how much of the total moles of this guy is actually mud contamination versus actual stock tank oil. So what we like to find is the guy in blue here. So if we just take this very simple equation and solve for xi stock tank oil, we then get the following relationship right here. And what we do in practice is actually to play graphically with this relationship or this parameter right here, Fg mud, until we see a straight line on the plot that we actually showed on the last plot right here. And just to go through that real quick with you all here, just to show that in practice, as we have a decontamination Excel sheet right here. Hopefully that shows up. And we can start with I think they're seeing here. This is not what we're sharing. Yeah. So I'll start with I'll actually just pick someone random. So I'll just ask Gerardo to come up with a suggestion on the F mud parameter that we just talked about to see if we can get closer to the actual straight line. So could you provide a guess on this FG or F mud? Sorry, this.
Yeah, just go ahead with 50%.
50%.
Yes.
I need to change this exercise because that was exactly what happened last time. And that's actually the right answer. So it's a too simple answer. That's what I found. But to illustrate,
there's some cheating going on here.
I got an eagle eye.
That's actually the answer. Yeah, but that's good.
But maybe you can explain why we are looking for a straight line.
Yeah. So we'll Bilal can make that comment in a second. But what I would like to just convey here is, okay, this is a synthetic case with perfect data, and we see a straight line here. But even with perfect data, if I said that this was 0.51, it would be very hard to differentiate that from, for instance, 0.49 or 0.48, even for that matter. And that exercise, that graphical exercise, is also prone to errors and uncertainty. So when you get a laboratory report that reports the decontamination level or the contamination level with 16 significant digits, you should of course remain a little bit skeptical. And here, Hans,
do you always assume a straight line in your reservoir oil? But that is not true. But you always assume the straight line that you have from C10 to C36 or C30.
Yeah, that's a very good question. And Bilal, you had some comments on that.
So the reason why generally we are looking for a straight line because we generally believe that if you have a decontaminated sample and if you plot that molar distribution of the decontaminated sample, that will be a perfect exponential model. An exponential model means that it will be on a log of on a semi-log plot, it will be a straight line, the distribution of these heavier ends, and that's generally an assumption in doing this, but that may not necessarily true, as Hans is saying, because but that's what, like, for example, if you look at PVT sim, the only molar distribution model they have is the exponential model, and we will go through, like, that's the next topic, like molar distribution models, and we will go through what is an exponential model, what is the gamma, we will also go through gamma distribution model, which is a more general model which doesn't assume that it should be an exponential model. You can have any distribution, and generally, like the software we use, Spacecom, you can do this decontamination calculation there, and there when it does this decontamination calculation, it tries to find this f of mud, which the value of f of mud that gives a distribution that follows a gamma distribution model.
Just a comment here. I don't know if you come into uncertainty in this, because we in Equinor internal, we have in some cases when we are using a program with gamma, we're using the straight line, we're using an exponential or something like that. We can see that, especially if we have very lean gases. I have one example. I get differences between 7-8% to estimate the contamination.
Yeah.
And which should you believe on? Yeah. Which one is the best one? You don't know the truth at all. But different methods with different kind of if you straight line, if you say gamma distribution, an exponential, and so on, or skimming technique or something like that, you can get very differences. So there's no it's subjective, and it's not a true value, and you have to discuss the uncertainty on that, maybe. Yeah.
And that's a very good point, Tristan, and that's also kind of what we would like to convey with this and these values that is sometimes reported, mainly from commercial labs that we work with, that people should not take that 4-digit number as the truth. And Curtis, you had a comment there.
Yeah, I think the laboratories use this graphical method, essentially what we're looking at here, with the assumption of an exponential or semi-log straight line trend, basically trying to get the points with the components with oil-based mud content to fall on the straight line. I think that's what the laboratories are using in general. So that gives you a starting point, an estimate of the mud fraction. What we do internally is more sophisticated, like Bilal was talking about, where the molar distribution shape, which we'll come to later, that will give a curve instead of a straight line on this plot, is known from other samples that have no oil-based mud contamination. So we actually know the molar distribution, be it exponential or non-exponential. For example, a biodegraded oil might have a very hump shape itself, the reservoir fluid itself being biodegraded. So you have an increasing amount up to C11, and then it starts decreasing. And you want to superimpose that reservoir distribution together with an oil-based mud distribution to get a composite distribution. Well, you need to know both the reservoir fluid molar distribution and the oil-based mud molar distribution. The laboratories don't have that information. They just make the assumption that it should be smooth. These components with oil-based mud should fall within the trend before and after those components. And they use a straight line as a guideline. So the labs can't be expected really to do much more than this. But the engineering of finding out how much it should be, and in your case, you're mentioning 7% difference depending on how you assume the reservoir molar distribution is. It might even be bigger than that if you have a biodegraded oil. So the answer is that you need to know the molar distribution shape for the reservoir fluid and the molar distribution shape for the oil-based mud to understand a composite of that. That's controlled by FMUD. Software like PVT Sim, most of the PVT software don't let you do that because they don't have the molar distribution, the generalized molar distribution model for the reservoir fluid. So if it's, in some cases, it's very important. You mentioned one case where it had an effect of 7 mol% mud contamination plus minus. We've seen even larger amounts difference between what the lab reports, assuming an exponential, and what the actual reservoir fluid distribution has. So it's complicated, but I think for the lab numbers, you can't expect too much more from them than what they're giving you.
Good point, and I'll come to Gerardo's question as well. Just again, when we introduced this topic now, we said that this is how most of the laboratories are doing this graphically. But there are more sophisticated ways to do that we will probably maybe touch a little bit on, at least to get a taste of that when we talk about these molar distribution models. But on Hans Christian there on for this one sample that you talked about, it was a lean gas condensate or something like that. Did you have also samples with no contamination in that case, or did you only have contaminated samples?
We only have contaminated samples. One way to figure out this is to have a clean sample and then probably added some mud to see how the shape is. I agree that normally in the laboratory they're doing it that way, and if we're reporting it in the lab, I will doing it the same way. But of course, I have to do any comments, and I look at using different other programs just to see that this straight line is this is the way the laboratory doing it, and I think it's the only way the lab can do it. Yeah. And but when you get this result, you probably should, if you get if you have other programs and you have the mud composition and you have the contaminated composition reported by the laboratory, you can put it into yourself and you can do some other gamma distribution or exponential distribution over everything, but the lab is doing it that way in some way.
Yeah, very good, very good. Curtis, any comments on that before we jump to Gerardo?
Yeah, no, I think everything is clear now that it can be more complicated than what the lab assumes, and if it is, then the engineers who've gone to this course or have studied the problem can handle that, but you need an ability to describe molar distribution separate for the reservoir fluid from the oil-based mud. And each well may have a different oil-based mud. And in general, though, the reservoir molar distribution is uniform throughout the field in general.
Gerardo?
Yeah, no, just a comment on the oil-based mud. This is something I've noticed in the last few wells we drilled. How difficult it's actually to obtain an oil-based mud. It's not trivial in a way that we have taken samples right before the transfer on the boat, at the mud pits and at the mud shakers, and throughout the formation, just trying to chase actually what is the right oil-based mud to use. Because it's always very hard to define whether you have contamination on the pits at the platform. That happens quite often, and it's also very hard to define when you are going through multiple stack reservoirs. It's actually very hard to understand how much contribution you have on the contamination on the mud from the formations above if you end up taking the sample below. So. Yeah, I think there has to be a lot of attention placed actually as well on ensuring that what you decontaminate to, it's very clear by everybody. Yeah, that was just a comment.
Yeah, so this guy right here, essentially, there's also, we're also introducing uncertainty there because we, in many cases, there's uncertainty also to what is actually the mud contamination composition, I guess, or the mud composition in the first place.
Yes, that's
very good. Before we end this topic, Curtis, if you can just mention in a little bit just briefly, in the cases where we have only samples that are mud contaminated, how we would go about a scenario like that when we only have contaminated samples available, and we would like to do equational state modeling and kind of the decontamination exercise.
Yeah, in that case, we've had a couple of cases like that, one from Gulf of Mexico, one from West Africa, and we basically have as the regression to get the reservoir fluid molar distribution is done by you have the mud composition, you have the measured composition. So you back out, assuming some F mud, a reservoir composition, okay? And that reservoir composition is gamma model, is fit to the gamma model for each sample. And so what you'll find is that, or what we do is that we adjust the F mud variable and the shape variable of the reservoir molar distribution simultaneously. Each sample has its own F mud, but the gamma distribution shape is common for all samples. So we have one variable controlling this gamma distribution shape, but we have individual sample variables F mud. So that if you got 10 samples, you would have 10 F mud variables and one gamma molar distribution shape variable. That's the approach. And basically finding what gives the best overall fit of the gamma distribution doing that. So you find the 10 values of F mud and you find the single molar distribution shape factor. I don't know if it makes sense in words, but that's what we do.
The other thing on that, just a quick comment on, Curtis, is many places they say that, okay, if the sample is contaminated more than 10%, for instance, then you need to throw the PVT report. It's worthless. You can't use the data. Any comments on that?
Yeah, we talked a little bit about it yesterday, but when we're talking about the decontaminated molar composition, you can always use a decontaminated molar composition to help in your fluid initialization, mapping compositions, spatial variation of composition. Really no amount of mud contamination is too high. You can decontaminate that. One of the reports in the material that we give you is by Bob Mott and myself on doing a comprehensive study showing that that's the case, that you can decontaminate very heavily contaminated samples to get the decontaminated composition. So that's answer A. You can always use the decontaminated composition for fluid initialization. B, answer to the question is that if you have lab PVT data on contaminated samples, you have to have an EOS that contains contaminated or the oil-based mud components. And you can do the EOS tuning with that data. If you have PVT, you have it. What we prefer doing is if you have a large set of data from production sample, PVT samples, and PVT data, we'd rather build the equation of state with those data. You can do a PVT match of all data with an EOS that includes oil-based mud components, which is kind of another way that you can also do that. But so you can do it, and you should never throw away data. But you might choose to not use PVT measurements on highly contaminated samples. And what you're going to say, well, what's highly? Okay, well, it depends how much of this PVT data you have for samples that have no contamination. If you have a lot of that kind of data, I just basically wouldn't use the PVT data if it's 5% contamination or 50% contamination. If you don't have any of these PVT data with uncontaminated samples, you might weigh more strongly the PVT data with lower contamination levels. I'd still use them all. So you have kind of a decision chart on what data to use, how to emphasize it, how to weigh it, according to what PVT data you have. So there's not a simple answer. You basically, throwing out the data, you can always calculate the data without weighting it, right? Just to make the comparisons. So generally speaking, we don't throw out data unless we have just a rich group of uncontaminated PVT data.
Very good. So we'll we talked a little bit about the shape of a gamma model, for instance, right now. For those of you who don't know what that is, we'll get to that in details in the next session. We'll be after lunch with Bilal on that. The last topic we'll cover today before we'll take a break is
Just a question.
Yeah.
Regarding the last discussion, for example, your sample at the lab, and you know the contamination, for example, 60 or 70%, and you have a decision whether or not to go with the PVT experiment. Would you go for the PVT experiment knowing the contamination level is so high, or would you prefer for just trust on the theoretical PVT sim kind of simulations or calculation? What would you pick up as
Yeah, so the question is spending money on PVT lab tests.
Yeah,
Contaminated
is it worth it by knowing that it's heavily contaminated and %, for example?
Yeah, you know, it's very simple. If you have reliable PVT data on samples with lower contamination level or zero contamination level, don't waste your money on getting new PVT data on this what's highly contaminated samples. I mean, if you have this data already, or low contamination levels or zero contamination levels, I wouldn't spend money on getting new PVT data for these very highly contaminated new samples. If you don't have any of that other kind of data, the only data you have is with samples with 50, 40, and 30% contamination level. Of course, you have to do measurements, PVT measurements, to get a preliminary equation of state that's definitely better than the predictive equation of state from any of the software. So the answer may be yes, get the data if you don't have any other data. No, don't get the data if you have a lot of the other kind of data. So that it's really it's not a yes or no question.
Perfect. Gerardo?
Yeah, this is more just a question I have. I mean, we're trying to work out, this is for Friday maybe, but you know, we companies, we collect all these samples, right? And then we do all the tests, and then you know, some of them they go to storage, and over the years they accumulate an outstanding amount of money of being kept in there. And of course, you know, when you go and you ask, should we throw it out? There's always a fear of throwing out data. But
yeah.
But there has to be a balance in that, right? You can't keep storage bottles that they amount for a well cost, you know. So I would like to see if maybe by Friday, if you could give us an indication of what would be your QC guidelines of when do you say, okay, enough is enough. You know, now I think that, you know, I'm in a good position to throw my samples. I think I covered pretty much everything that could be done within the next 20 years. If there's any new development, or if I decide to, you know, to inject gas, you know, of course, covering all the surprises that you have along the way of a field development. Thanks.
Yeah, that's an excellent question. I think we get in every single course we have on this. And Curtis, you have a very good answer to that question. So I'll give you.
Yeah. Again, it depends how much data you have already and of what type. So if you have a rich amount of data, maybe even some gas swelling data for potential gas EOR projects, and if it really depends what available PVT data you have already. And if you have very little, then you may have to pay for some storage for a period of time. And if you have a lot of data, don't save the company money or get yourself a bonus, or don't waste the storage charges. It really has to do mostly with that. I think that's is the short answer. What's enough data? You can discuss that and argue that, but bottom line, that's it. If you've got a lot of data, but let's say that you've got a lot of data, it's rich and everything, and you drill a new well and it enters a new horizon and samples new sample with 40% contamination, but it's a new horizon, a new zone. Okay, it's like a new discovery. Well, relying on all that other data from the other zones probably is not a good idea. There you would go ahead and collect data, PVT data, and you might do storage because you have zero data.
Yeah.
So that's basically I think this is your short answer.
And do you see any justification for keeping PVT data? I mean, you have PVT bottles on storage for many, many years. Or have you seen any aging effect that will affect the properties anyways?
We haven't looked at a lot of old live samples. We had a recent discussion with John Radulowski, and we have a dialogue going on with him on some of the other questions from the course. I'll drop that to him again. As I recall, when we discussed this recently, he said that Shell and Schlumberger, who he worked for, D.B. Robinson and Shell and Schlumberger, over a 35-year period, I think he mentioned that they had on occasions gone back to old live samples and used them with success, and on occasion gone back and found PVT anomalous data. So there wasn't an answer to that. So it's expensive, live sample storage over long periods of time. Surface oil samples, completely sealed, those are great to keep for long periods of time. I mean, they have to be really sealed properly, but those are the kind of things that you can come recreate live samples. You're basically maintaining the heavy ends, which is the unique part of the reservoir fluid, in a container at atmospheric conditions in a closed container. You can always reconstruct something that's close to original fluid to do various studies on later. That's a much cheaper, more inexpensive, and probably equally reliable way to do it, I think.
Yeah. Okay, thanks.
Just on that, Curtis, wouldn't you say that if you have a full suite of PVT experiments done on the reservoir fluid composition early in the, or like some kind of reservoir representative fluid sample early in the well's lifetime, that it's in general very, very hard to justify keeping a bottle for later. Even gas EOR, for instance, that's not you don't need an in situ representative fluid sample to do successful gas EOR experiments in the laboratory. So then you can just sample that later if that becomes relevant in the future.
Yeah, that's right.
And I think like it's this what the companies are trying to, like, they're playing on this fear of people, because we sometimes we don't know better that you need the samples maybe for later, maybe you want to do this and this and that. But if you have a good suite of data very, very early, it's very, very seldom that you can justify keeping them, but they're just playing on this fear to I guess
I think Matthias rightly mentioned, because one reason why people usually go for storage is people generally think that in situ representative samples, or the samples taken early in the well's life or the field's life, they are the most important sample, and then they just have to store the samples and just use it later when they need some PVT experiments. But yeah, like all these experiments, like for example, gas EOR type experiment that you may need later, you haven't decided yet whether you will go for gas injection or not. Those experiments can easily be done on samples that you may take later in the field's life. It's not necessary to have in situ representative samples and save them and like paying for all the storage every year to these service companies for long periods.
Yeah, especially if you're a large company as well. Like if it comes that one case where you actually need it for some reason that I can't come to think about, but let's say there was a reason where you would like to have some samples. I think the fact that you save on these other costs will easily justify the fact that you, in that one particular case, did not store it. So, yeah. But that's a good question. We'll try to cover the last part here before the break. It's going to be fairly quick, but it's very important, and it's about what we talked about yesterday. Do you still have a question, Gerardo, on that? Or was it okay?
No, it's okay. Thanks.
Perfect. What we talked about yesterday, we've been talking about it today. We're going to talk about it also tomorrow in C7 Plus characterization, is capturing this relative paraphenicity and aromaticity of a particular field. And I think yesterday you did the calculation of the Watson characterization factor for these two PVT reports that we have. And you can just plot the measured molecular weight and the densities of the entire stock tank oil, but you can also back calculate properties to make, and we've touched upon it a few times. It's that the properties for molecular weight and specific gravities reported in commercial laboratory reports are most times these cat spheres of body numbers, which are, as we also mentioned yesterday, more or less arbitrary. Okay, they might not be representative for all the fields in the world because this specific gravity molecular weight relationship is a function of relative aromaticity and paraphenicity for a particular field or a basin. And especially the absolute heaviest molecular weight and specific gravity is in the way that's calculated is sometimes very arbitrary and prone to a lot of error, and is also different from lab to lab. So the first thing to mention is that actually back in the 80s at least, Core Lab used to report the measured molecular weight of C7 plus and specific gravities of C7 plus for stabilized oils. So that's typically stock tank oils. Now, what is the standard in most of these PVT laboratory reports that everybody in the course that works with PVT lab reports need to be aware of is that when you see a molecular weight C7 plus and a specific gravity C7 plus, they're just calculated based on these cat spheres of body molecular weights and specific gravities. And we'll show an example of that. While the problem with this procedure is that you use values that are just from some kind of correlation to calculate these properties and not actually measured values for molecular weight and densities or specific gravities. But there's a trick that we use, and we spend a lot of time on this and this plot for every new field that we work on. It's like Watson characterization factor is almost the first thing, and then creating this plot with back calculated molecular weights of C7 plus and specific gravities is what we plot. And the trick there is to make sure that we only use the measured total molecular weight and specific gravities of the oil, which is in many cases not reported in these lab reports. But it's very often measured. And the reason why it's not reported is because the laboratories doesn't like all the questions that might arise if you report two numbers of the same property. So if you report the calculated C7 plus molecular weight and the measured C7 plus molecular weight, you have to also answer the question of what is the difference from that. So when we talk to some laboratories, they just for simplicity just is reporting the calculated value, even though they measure the total.
Yes, we have some discussions, especially with the Schlumberger lab, that they don't measure the molecular weight; they calculate it in some cases. Yeah, so that's an issue. We have had a lot of discussion with them. Told them that they have to measure the molecular weight, even if they can use it, the calculated one, but they should measure it and report the measured one.
Yeah.
But we've seen that some laboratories, especially Schlumberger laboratories, that they do the calculation.
Yeah.
That's because of the HSE issue with the benzene or something like that. They told us. Okay.
Yeah. Yeah, but it's that's a very good point from Hanser. We have also seen that with Schlumberger and Core Lab reports database, but they're many times not reporting it in the report. So to get the measurement, you need to ask for it specifically. But I think we as a technical community can push this awareness onto the lab that we know what they're doing, and that we can get them to start to report this value, and because there's a reason for this inconsistency. So yeah, but in some cases, definitely they're probably not even measuring the molecular weights. There was a question here from Gulnar that this is on the stabilized oil. So that's a very important point, because the measurement of molecular weight and this the density guy right here is done and only relevant on stock tank oils. So for the two reports that we have a flashed oil for the black oil case. That will be the flashed oil, and in the gas condensate case, it is actually the flashed separator oil. So when they've taken the separator oil and flashed that to stock tank condition, so there's a flashed oil which is from the separator oil, essentially, just removing the gas that comes out of solution. So that's where you get this data. So typically, when you're dealing with a report, the number of data points that you have is typically equal to for this plot from one report is equal to the number of stock tank oil compositions that you have reported or available. Yeah. The density measurement is usually very accurate, and as mentioned earlier, this measurement of molecular or average molecular weight, there's the benzene freezing point depression method. It has a high uncertainty, sometimes 5 to 10%. So of the two, that's the most uncertain. Just before we take a break, and then just after the break, we'll just go through the exercise on this, which will be real quick. But our recommendation is, when you are talking about molecular weight C7 plus and a specific gravity for the stabilized oil, which is exactly what Curtis mentioned, what is important, because it has all the heavier components, which makes one reservoir unique or to differentiate potentially from another field or basin. And the way this back calculation is done, for those of you who are interested in that, just send me an email. I can send the derivation of these formulas, but it's fairly straightforward. What is important to emphasize is that these equations, compared to the ones that we just looked at, they're only using measured values. So the weight percentage here is measured. The measured total molecular weight is measured. These guys right here, that's the molecular weight from for the known hydrocarbons. So that's everything from C1 to C6 and CO2, H2S, and nitrogen. So we know the molecular weights of those because that's from pure compounds. So we either use known quantities or actual measured quantities. And the same goes for this guy right here. This is actually measured. And this guy's measured, and these guys are known because they're based on pure components. This is given to us by Mother Earth. And just to highlight the difference again, there is that these guys right here, they're actually calculated or estimated from some correlation, essentially, which is what gas phase body is. It's like a correlation. So that's a difference there.
So that sum includes all the fractions, including C7, C8, C9, and under C36 plus.
Yeah, exactly. So this goes from C7 to C, for instance, 36 plus, and that's C7, and I guess the higher the carbon number or single carbon number component, the more uncertainty it is actually in this, and potentially how much more can it deviate from specific gravities and molecular weights. This, just to wrap up this brief section, but I think is an important part, which is how we correctly will back calculate molecular weight C7 plus and specific gravity C7 plus with this particular formula here in the PVT reports, because that's typically not done for us. And as we mentioned, the reported molecular weight C7 plus and specific gravity C7 plus, they're just calculated based on these, arbitrary values, sometimes from Casper's body, and maybe also sometimes from this Whitson table we looked at the first day. So the exercise 10 that we'll just do together now real quick is to show the difference for the two PVT reports we have attached in this course between the calculated, direct calculated way using the Casper's body numbers and actually back calculating based on the measured values. So everybody should have gotten this Excel sheet with molecular weight C7 plus and specific gravity C7 plus. There are for each sample there will be 4 values or 2 values to calculate. This is what we see on the top here is the so-called wrong or not recommended ways of calculating it, and that's just straightforward using the formula right here. So we use weight percent and not mole percent because that's what's measured in the stock tank oils. And if I remember this correctly, it's the sum of the weight percentage higher than C7. We'll start with the that shouldn't matter. Divided by the sum product of the weight percentage right here, and then 1 divided by the molecular weights, which is what we calculate first. I think that should be correct. 264. Hope that's correct for the people has the report. We can double check it maybe. So in the report,
You don't have it.
huh?
You don't have it.
No, it's not provided.
No.
No. Okay, so that's not in the report. That's good. And we do the same. We use the formula to the right here to do the same way. So this is again the wrong way of calculating. So maybe not the best thing to do for education purposes to teach you how to do it the wrong way, but that's the way people are doing it at least. So again, we take the weight percentage heavier than C7, and we again use the sum product function of the weight percentage, and then 1 divided by the specific gravities. And you can do this for both the oil, and you can do the same for the gas condensate, and you will get these values right here. But we'll try to emphasize the focus on the correct ways of calculating this. Or actually here, this is the total. No, okay, yeah. Very good. And then we'll focus more on the back calculated way of obtaining the C7 plus molecular weight and specific gravity values using this formula right here, which is in the formula sheet on page 3 or 4, and also in the slide deck that we just went through. And we can start with the C7 plus molecular weight. And we start with the oil. And then we divide by the measured molecular weight, or 100%. So this is just the total sum of the entire sample. So that's actually this number right here. And then we divide by the measured molecular weight. And then we do the sum product of everything. Up until this point, then 1 divided by molecular weight. Yeah. 261 is what we get, and it's actually the exact same formula, or the function is the same. We just have to change the molecular weights with the specific gravities, I think. Yeah, and we get 0.849 as the back calculated values. And we can first of all compare the difference. So the molecular weight of C7 plus here is 261 versus the calculated with Gatsby's body 264. And we also see the difference when it comes to the specific gravities right here. And in the lab reports, depending on what field you're working in, it can be smaller or most times larger differences than what we see right here.
And like one reason why you see small difference here is because like we went through this Watson characterization factor value, and we saw that it's very close to what generally is expected for the Gatsby fluids, the fluid system they use for the measuring of these molecular weights, very paraffinic. So that's why for this fluid system, maybe this Gatsby molecular weight and specific gravity are reasonable compared to many other fluid systems you have in the world. But we will see tomorrow how we can develop this individual component molecular weights and specific gravity correlation as part of EOS model development. That will be a main exercise tomorrow.
Very good. So again, I just did it quickly as the same formula I just applied for this fluid, which is the gas condensate fluid, and we get these numbers. And just again, comparing them, they're not the same. That's the first time thing we see, both for the molecular weight C7 plus and the specific gravity. And as Bilal said, the reasons why they're similar is because they're more close to the general Gatsby's body. In this case, which sometimes is just arbitrary, and sometimes it can be very, very large differences as well between the two. And we'll emphasize the importance of developing this relationship and plotting these points and actually back calculating them more tomorrow. But before we leave this topic, if there's any questions, or while we're people are thinking about some questions there, unless Curtis has actually done the donut field story, it would be great just for an example there, Curtis, to emphasize the importance of developing this relationship and calculating these values for a particular field for EOS fluid characterization purposes. Would you like to share a few words from that?
Yeah, this was probably the most extreme case where getting the characterization of the oil, express it in terms of the Watson characterization factor, correct, had a huge impact on his study. So I can tell you a little bit of the story. This is probably 20, maybe 25 years back, and it was in Dubai. There's Phillips was operating a field that I call it the donut field. It was kind of shaped, had kind of unusual round shape and a depression in the middle, and they were doing gas injection and had a phenomenal amount of new PVT data. And for gas injection together with depletion, it was a volatile oil, and so they were going to do this gas EOR study. And there was a relatively young engineer. He had kind of self-taught himself the A's, all the methods of doing an EOS model characterization. He was using the software PVTX, which Phillips leased back then. And maybe he'd gone to one of my courses, I don't remember, I don't think so, but he had learned the software and he had all this data, he was responsible, and he developed this equation of state that really did a great job of fitting the vast majority of data, including the more complicated PVT data, the gas injection. And so I was in the area and he asked me to drop by for a day to look at what he'd done and to discuss it. So before lunch, we kind of went through the data and we looked at the equation of state predictions. Everything looked great. And then he showed me the tuning parameters of how much he had changed the critical properties of the C7 plus components, TC, PC, acentric factor. I don't remember the exact parameters that he changed, but it was basically the properties of the C7 plus fractions, maybe some bips. And I started looking at the amount of correction he had to these properties, and they were like just huge. I mean, 20, 30, maybe 40% change. And it was curious, and it was just before lunch, and I said, well, I'd like to kind of look through it through lunch and try to understand why you were having to change the parameters so much to get this match. And so went through the day, looked at some of the data, and came back during the lunch break. And basically, the first thing I did was calculate this Watson characterization factor just for orientation on one sample, and then the second and the third sample, and it was like 10.2. It was in the low 10s. I don't know if I'd ever seen something that low, which meant that it was a very aromatic oil. But for some reason, he had gone in with the base characterization, assuming Katsura Zavadi. In fact, I think what he had done, he'd literally put in all the properties from Katsura Zavadi as the starting point for calculating critical properties and so forth. Table 5.2 in the monograph, if you want to look at that. Basically, he took those as starting point properties. But that's, as we saw a couple of days ago, that's basically the Watson characterization factor for all those single carbon numbers around 12, 11.8, 12. And even though it was the average C7 plus molecular weight gravity that gave this low 10 Watson characterization factor, very aromatic oil. But basically, through all this regression, he'd been able to tweak all of the TC-PCA centric, all these properties into aromatic-like properties. And so when he came back from lunch, and I said, well, I think I understand why you had to change the properties so much. And I just showed him the Watson characterization factor calculations and so forth. And I said, well, let's just do an experiment real quick. And let's just use the default software characterization that will fill in the TC, PC, and acentric factor based on the specific gravity molecular weight single carbon number relationship. And by default, PVTX what it would do is that it would find that curve that we looked at yesterday that gave a fit, an exact fit of the measured C7 plus gravity molecular weight. So he put the samples in and he basically turned on this characterization factor, which filled in all the properties by default, and did the calculations, had all the data already input, all the experiments and everything. He just did kind of a prediction run, and without any tuning. And it wasn't better than his, but it was basically on top. The predictions were very close to being on top of his. And I think he had used a year of work developing this EOS model with the tuning, the regression, and everything, and making all these major changes. And I wasn't sure if he was going to go him early. He was kind of like, in one way, depressed because that one, you know, I don't know, issue had you know, basically starting with the cat sphere as a body, assuming that you have this vanilla envelope fluid, was so wrong. And had he used a more aromatic set of properties, he would have gotten this prediction that required very little tuning to get the final EOS. Anyway, that's it's a true story, and it's kind of a most extreme case of where. So I think what I want to bring as a what's the conclusion of the story here for this course and where we're at in the course is that the predictive EOS, what you basically start with as before you start doing any regression, it better be giving you reasonably accurate predictions for pretty much all the data. Maybe it won't be predicting the critical points of you know, swelling test data. Maybe if it's near critical samples, it'll predict a bubble point instead of a dew point on some of the samples. But the overall prediction should be pretty much reasonable, okay? And if they're not, that's a huge red flag. And with pretty much any of these software programs, the default characterization should get you ballpark predictions, with the exception of these more complex, you know, near critical phase behavior, from the get-go. And if it doesn't, it's kind of a red flag. And about the only reason that it wouldn't do it is that you've got this wrong starting gravity molecular weight relationship that's saying it's too paraffinic or too aromatic. And if you get that, if you adjust that and go through the, you know, the methods to get that right, then get some predictions that are very ballpark good starting point. The whole experience of regression and tuning will be a much more simpler, and it may not be simple, but it'll be easier and more successful. That's the end of the story. I think that's the carryover. So it's
very good.
I will just add some comments here on what Curtis said. So whatever Curtis said, like developing this molecular weight specific gravity correlation for developing EOS model, that's very important, and that's we are gonna see tomorrow when we will be doing or developing our equation of state model for this fluid system. But what Curtis has said, that if we do like proper C7 plus characterization and develop an equation of state model, and that the EOS model without any tuning, that initial EOS model should give us reasonable predictions. And how we can make sure that we have done proper C7 plus characterization, we will also see that tomorrow when we will be doing the exercise. But that's like we went through all the lab experiment QC, the different methods. But when we develop the equation of state models, this initial EOS model with proper C7 plus characterization work, we also use it as a guidance to see how good the quality of PVT data is. So maybe you have done the right C7 plus characterization and you have developed a good initial EOS model, but that EOS model may not be giving you very accurate predictions of the PVT data. And in that case, you may have quality issues with the lab PVT data, because there are always some tricks that you can do to close the material balances that we had been seeing before. And you may, like on the material balance, all the data look very nice, but when you start doing the prediction with that initial EOS model, you may see that some of the data or some of the PVT samples, they may not be falling in line with your equation of state model predictions. And there you can start highlighting, okay, what are the quality issues and which part of the particular experiment, which PVT data of a particular experiment is questionable from the lab.
Very good. So Remember that always to back calculate based on measured molecular weights and specific gravities, such that we capture that potential change that Curtis talked about from potentially in more paraffinic fluid to something that potentially can be very aromatic in this case, or something slightly less dramatic as well. Very good. There was a question here. Would we be talking at some point about merging measurements from GC and boiling point or true boiling point distillation data, i.e. using lighter fraction from GC and heavier for TBP tests, if we have a spreadsheet that could share so this is understood? So that's a good question. So in the studies essentially where you have both the GC data and boiling point distillation data available, how are we using that in practice, and how would you use this into, for instance, developing a C7 plus specific gravity molecular weight relationship? Curtis, you want to answer that quickly?
I think Bilal can probably comment on that. I can add some.
Yeah. So actually, there is not a straightforward answer to this question, because there are different tools and techniques how you can integrate the TBP data and the GC data together for C7 plus characterization, and like the tools and techniques that we generally use for this kind of analysis, that's something we are going to discuss tomorrow when we will be developing the field-wide equation of state model. For this particular course, we are not going to use any TBP data for the EOS model development, but the tools and techniques that we are going to discuss tomorrow, that can easily be used if you have TBP data together with the GC data. And I think this like very specific answers to this question, I think those will be more relevant for tomorrow's session when we will discuss these things.
Very good. So we'll continue on that tomorrow. Very good. Gerardo? Gerardo?
Yes, yeah, microphone off. Yeah, we normally work with a lab that is giving us the C7 plus molecular weight. In that case, you will be using that, right? You will be using the measured one and not the back calculated one that you just mentioned. Is that correct?
So yeah, you'll never measure only the molecular weight of the C7 plus molecular weight. The thing that you'll measure is the total stock tank oil molecular weight number, and then if there's any property provided by the lab on C7 plus molecular weight for that stock tank oil, that's, I think, almost now a standard most places that's calculated number, and you should not use that number that they're giving, because that's based on cat sphere as a body. You should use the number that you back calculate from the measured value, and sometimes this measured value is not provided by the lab, so then you need to call up the lab and make sure that they report that in the report, because that's a very, very important number.
Yeah, but yeah, so sorry to insist on this, but I remember specifically asking the Stratum lab, right, if they have the molecular weight C7 plus is measured, and they reply, yes, it's the C7 plus molecular weight is measured with the freezing point depression way.
Yeah, so Gerardo, I think you are talking about the study we were doing together.
Yes.
Yeah. So yeah, I think there was a misunderstanding like on the lab side, because when I think it was Mo was doing the study, and when he asked them, like, did you measure the C7 plus molecular weight? They said yes, and then when he insisted on this question, and he said, did you measure the C7 plus molecular weight or the average flash load molecular weight? And then they said, okay, yes, we measured the average flash load molecular weight and not the C7 plus.
Okay, so it was a wrong communication from Stratum. Yeah. Okay, thanks. That's clear now. Thank you.
Very good. Any other comments? And Christian, I saw you had your mic.
Yeah, but they said that what I was thinking about, they measure the average and then they calculate the C7 plus based on the composition. Normally they using what they call the PNA, because I was working at Stratum Lab and Res Lab 10 years ago. And then we're using the PNA distribution. It means that you calculated the C6, C7, C8, and C9 molecular weight based on the composition.
Yeah.
So that is more accurate than cat sphere's body, and that you're using that values to calculate the C7 plus. So that is normally a little bit more accurate than C7 plus that you get if you're using cat sphere's body as the pseudo component.
Yeah. Very good. Yeah. And the story on that is that number is very important, and you should make sure that you get the true, at least the number that you're using in analysis should be based on actual measurements from the field that you're working on, and not some random correlation as, for instance, cat sphere's body or something else. Very good.